Hello and welcome to a ForeFlight presentation on weather briefing tips every pilot should know. My name is Scott Dennstaedt. I'm a CFI and former National Weather Service research meteorologist, and I'm also ForeFlight's weather scientist. Now today I will be presenting 5 topics that every pilot should be comfortable with. I want to provide you with some background and details that will help you understand how to effectively use this in your day-to-day pre-flight planning. I'm going to start out first with a discussion of Terminal Aerodrome Forecast, or TAFs, and we'll move into a discussion of AIRMETS, and also talk about a newer product called Graphical AIRMETS, or AIRMETS. Then we'll end with a convective discussion, specifically talking about Convective SIGMETS and how to minimize your exposure to convective turbulence. First on the list is Terminal Aerodrome Forecast, or TAFs. Now TAFs are one of the most detailed forecasts issued by any meteorologist, which means it's actually pretty useful to pilots. And it's the most popular forecast used by pilots in their pre-flight planning. So to find TAFs in ForeFlight, you simply tap on one of the markers in the map view. In this case, I'm showing the flight category markers. By tapping on one of those markers, it'll bring up this popover you see on the right. And in that popover, you'll see a forecast tab at the bottom. You tap on that, and that will bring up the TAF for that particular airport, including a decoded version below it. Now, for some reason, that particular airport doesn't have a TAF. You may see nearest TAF instead, and that would be the nearest TAF to that airport. Now, TAFs are issued by meteorologists at the local weather forecast offices. And this is quite important because they have local knowledge of the weather. They forecast day in and day out in that particular area, so they're very comfortable with the weather for that geographic region. Now on the right, you'll see a map here of all the county warning areas. Each one of these warning areas basically has a weather forecast office located within it. And so all the airports within that geography are issued by that particular weather forecast office. Now, a terminal area is a region within a 5 statute mile radius from the center of the airport's runway complex. Quite small. And as a result, forecasters consider a TAF a point forecast. It's a very, very small area to forecast for, which makes it quite challenging from a meteorologist's standpoint. Now, the terminal area's vicinity is not all that much larger. It's a donut-shaped region within a 5 to 10 statute mile radius of the center of the airport's runway complex. But it does not include the 5 statute mile area that represents the terminal area inside. If you look at a TAF, you'll see some forecasts for the vicinity, including showers in the vicinity, thunderstorms in the vicinity, and fog in the vicinity. Now, when you think of TAFs, you really have to think of tiny. TAFs are not a zone or area forecast and really should never be used as such. So for events such as fog, thunderstorms, freezing rain, that tiny area may sway a forecaster to exclude some of these events when the uncertainty is rather on the high side. So a good example is I was making a flight from Charlotte, North Carolina, up to Baltimore, Maryland. And this is the view of the XM satellite weather picture before I departed. Now there are definitely cells out there, and sure enough, when I departed, I had to deviate around a lot of larger cells and even a couple thunderstorms along the route, but none of the terminal forecasts along that route had any indication of thunderstorms. Now is that because it was just a bad forecast? Now, as we'll see later, uncertainty makes it very, very clear that small area, that tiny forecast area, may not be hit. They won't put it in the forecast. And so here's a few thunderstorm hints that I want to present to you. First of all, when thunderstorms are a possibility, but a little bit on the uncertain side, a lot like the image I showed in the previous slide, you'll likely see a forecaster use rain showers or showers in the vicinity instead of thunderstorms and rain. Now, showery precipitation is still a convective process. Most pilots don't understand that, but forecasters are often pressured by airlines to avoid putting thunderstorms in the forecast. And this is primarily because as soon as that happens, the airlines basically have to follow an alternate and carry extra fuel to get to that alternate. So how do we know all these kind of details? Well, the secret is in the AFD. No, it's not the Airport Facility Directory. The Area Forecast Discussion, or AFD, isn't actually a discussion about the area forecast either. It's a plain English discussion that's created by the same forecaster who issues the TAF for that particular county warning area. So these are based on a county warning area for a particular local weather forecast office. So it really discusses the weather for that local weather forecast office's county warning area, and not for the area forecast that has the Miami, the Boston, the Dallas-Fort Worth, Chicago, Salt Lake City, and San Francisco. It's not that area forecast discussion. It's for the county warning areas. And it's a really loose format. It's a plain English kind of thing. It contains a synopsis section, near-term, short-term, and long-term discussion. So this even helps you with what's happening in your particular area, even several days in the future. And so every AFD should also have an aviation section that discusses the TAFs for that county warning area. And this is where the forecaster can put in details that they can't put into the TAFs. So the AFD may actually have a lot more information in there that is very useful to pilots. So I always say if you're not reading the AFD, you're missing half of the information for a TAF. So let's take a look at an example. Here's a TAF for Charlotte Douglas Airport. And look at the second line there. This is from 1600 all the way through 000. And you'll notice that there's some somewhat gusty winds, better than 6-mile visibility, but showers in the vicinity, and a broken ceiling at 7,000 feet. Now, high base rain showers in the vicinity with good visibility below doesn't really appear all that threatening, even to a pilot flying VFR. But you have to read the details of the terminal or the AFD to really understand what's going on. So I pulled out the area forecast discussion for the Greenville-Spartanburg Weather Forecast Office, who issues the TAF for Charlotte. And here's what it says, highlighted in here in yellow is the important part. It says scattered showers and perhaps a thunderstorm are expected across the North Carolina Piedmont from the afternoon until early evening, and will carry VCSH for now to cover that threat. So again, it's a discussion that's kind of free form. The forecaster can put in that discussion anything that would help you more detail in figuring out kind of what they're thinking from a terminal forecast standpoint. So showers in the vicinity were just a placeholder in this case. It turns out that thunderstorms did roll into the Charlotte area eventually during this time, but the certainty wasn't there at the time that the forecast was made. So this allows them to quantify their uncertainty, which really helps pilots figure out the details. So where can you find these AFDs? Well, of course, that's the $64,000 question. Well, it's not in ForeFlight as of yet, but you can go to aviationweather.gov to get the aviation section only of the AFD, and you'll see a selection under the Forecast tab for AVN Forecast Discussion on aviationweather.gov. Or the easiest way to get the entire AFD is to just visit weather.gov. When you bring that up, you'll see a little data entry window in the upper left. You type in the airport identifier for that particular county warning area you're interested in. Tap on Go, and that will bring up, you'll see on the right side there, down a little bit further, bring up a page where there'll be a link to the forecast discussion. You click on that, and it'll bring up the complete discussion, the latest discussion for that particular county warning area, which covers that particular airport. Now, I always get a lot of questions about the difference between model output statistics that we added in late in 2014 versus the TAF itself. Now, on the left, you have the terminal forecast for Oshkosh. Now, during the EAA, they actually issue a terminal forecast, and it's a part-time TAF. And we took a look at one evening what the TAF was suggesting versus what the MOS was suggesting. And you can see from 10 p.m. to 1 a.m. Central Time for the TAF, the forecaster was looking at a marginal VFR situation with thunderstorms, heavy rain, and cumulonimbus. However, the MOS for that same time period from 10 p.m. all the way through 5 a.m. had no indication whatsoever that any thunderstorms would occur and that the atmosphere would stay essentially VFR. Well, it turns out in this particular case that the MOS was actually right on the money. In the case of the TAF, the forecaster evidently took a little bit of a meteorological risk here, and unfortunately, because of the size of the terminal area, bit that forecaster. This happens quite a bit, but still the TAFs are usually probably the better of the two. So if there's a TAF at that airport, you should always use that first and use the MOS as a supplemental piece of information. And of course, not all airports have a TAF, so MOS provides good input for those kind of airports. All right, let's move into a discussion of AIRMETs. Now, AIRMETs are issued by forecasters at the Aviation Weather Center in Kansas City. They're advisories for widespread adverse weather, such as moderate icing, moderate turbulence, non-convective low-level wind shear, strong surface winds, IFR conditions, and mountain obscuration. Now, AIRMETs are issued 4 times a day and are valid over a 6-hour period. So they are a time-smeared forecast, valid over a 6-hour period. So given this lengthy duration, it may be that only a small portion of the advisory area may be affected at any one time by the hazard that is forecast. We're going to get back to that in just a bit and show you how AIRMETs help out in that particular area. But for now, I want to also present some details about AIRMET Tango. AIRMET Tango is issued for widespread moderate non-convective turbulence, which means they don't issue an AIRMET for thermal or convective turbulence. So if you're flying below some of these cumuliform clouds, like you see there on the right, and you're getting beat up with some moderate, continuous moderate turbulence, thinking, what the heck, they didn't produce a decent forecast. I didn't see any AIRMET for turbulence. That's because that would be convective turbulence, and AIRMET Tango is not issued for that. And one of the reasons for that is that, during the summertime, you'd have this big AIRMET from east coast to west coast during the afternoon, covering all that area due to the fact that basically all the turbulence is convective, and that doesn't help anybody out. So AIRMET Tango is only issued for non-convective turbulence. Now similarly, AIRMET Zulu is issued for widespread moderate non-convective icing. So same kind of issue, they don't issue an AIRMET for convective icing. So if you're flying around at temperatures below freezing, flying in and through some cumuliform clouds, vertically developed clouds, picking up an airplane load of ice, wondering why there was no AIRMET out for icing in that particular area, and that's because vertically developed clouds like cumulus clouds are convective, and AIRMET Zulu only covers moderate non-convective icing. All right, so Graphical AIRMETS, a fairly new product. It was introduced by the National Weather Service October 2008, and it was generally created to replace the AIRMET, a stepping stone towards the graphical forecast for aviation, and also the replacement, helping to replace the area forecast in the future. Now, AIRMETs are a little bit different than AIRMETs. They actually are not a graphical depiction of AIRMET. I've heard that many times. AIRMETs, we know that AIRMETs are time-smeared forecasts valid over a 6-hour period, whereas AIRMETs or Graphical AIRMETs are valid at a single time and represent coverage of that particular adverse weather element. Those are referred to as snapshots. They're issued by the same forecasters, but their coverage of that particular, whether it's icing or turbulence, at a single time. It shows you where that icing will be at a particular location and time. Now, Graphical AIRMETs, just like AIRMETs, are issued 4 times a day, again, by the same forecasters, with 5 snapshots for each adverse weather element. So I'm showing a depiction here in ForeFlight in the weather imagery under the Graphical AIRMET collection. You see I've got highlighted here the 5 snapshots for the AIRMET Sierra, or essentially AIRMET Sierra, which includes mountain obscuration as well as IFR conditions. And that consists of a 0 or initial forecast, a 3, a 6, a 9, and 12-hour forecast. Well, it turns out that if you take the union of the first 3 snapshots here, that actually makes up the legacy AIRMET. So that's what the forecaster does now. They create these snapshots, hit a button, and essentially the legacy AIRMET is a byproduct of this AIRMET. So the text is for that AIRMET is automatically generated from the graphics. So here's a good example that explains why AIRMETs can be so useful to pilots. So here's a legacy AIRMET for turbulence in ForeFlight. And this particular AIRMET, if you were to tap on it, it would say the valid time was from 21Z to 03Z, a 6-hour period. But here's the first snapshot of the 12 for AIRMETs for that particular event. You'll notice that the AIRMET area here covers most of the central part of Ohio all the way up to the Ohio-Pennsylvania border. And that's valid at 2100Z. At 000, you can see that that entire area has been shifted to the east, covering a little bit of Pennsylvania, western part of Pennsylvania, and just maybe a little bit part of the eastern part of Ohio. So you can see from the snapshots here that that area of turbulence is moving to the east with time. When you look at the legacy AIRMET here in ForeFlight, you really can't get that sense. And in fact, by snapshot 3, valid at 0300Z, you notice that that particular turbulence AIRMET is completely gone. So that area is dissipating. You can certainly look at some of the details of the text if you were to tap on the legacy AIRMET. And it does say at the bottom there that that particular area of turbulence is ending between 0 and 3Z, which is also represented in the last snapshot. But I think from an overall standpoint of being able to see each one of the snapshots really helps you understand where that particular adverse weather element is, where it's moving to, and whether it's dissipating or evolving. All right, let's move into a discussion of convective SIGMETs. Now, convective SIGMETs you'll see in ForeFlight represented by a red shaped polygon. There's one here shown off the west coast of Florida. Now, convective outlooks are a yellow polygon. Now, convective outlooks basically provide you with a sort of an overview of where the convective SIGMETs will likely be issued in a 2 to 6 hour period. So it's important to understand that convective SIGMETs are really active areas of thunderstorms. This is where the Aviation Weather Center issues these convective SIGMETs. They basically put a fence around those active area thunderstorms. So it really represents more of a nowcast rather than a forecast, showing you exactly where thunderstorms that are deemed to be a threat to aviation are located. Now, the convective SIGMETs are only valid for 2 hours, so again, it's more of a nowcast. Now, here's some convective SIGMET criteria that you need to understand. First of all, convective SIGMETs are not issued just for any thunderstorms out there. They have to meet a certain set of criteria, which makes them interesting to aviation. It certainly represents a danger. So anytime you have a single cell thunderstorm out there just by itself, it's pretty easy to get around. But when you put all those cells together in a line at greater than 60 nautical miles with at least 40% coverage along that line, then you'll get a convective SIGMET issued. That means essentially you're going to have a difficulty working your way through that line. You're probably going to have to go all the way around that line, which means essentially more fuel. So you certainly should factor that in. Anytime you have an area of thunderstorms greater than 3,000 square miles with at least 40% coverage in that area, you'll see a convective SIGMET issued. Again, pretty big area, which will require you to have additional fuel to go around that area potentially. Anytime embedded thunderstorms occur, regardless of the size, a convective SIGMET will be issued. And of course, severe thunderstorms also. Anytime the local weather forecast office issues any kind of severe thunderstorm warning, that will automatically generate a convective SIGMET. The forecaster will issue a convective SIGMET for a severe thunderstorm, even if it's a single cell, because we want to stay further away from severe thunderstorms. Now, convective SIGMETs are not generally issued for what are called pulse-type thunderstorms, or what pilots would call air mass thunderstorms. So you can see in the picture here on the right, these were all pulse-type thunderstorms, kind of spread apart, easy to work around, but certainly there was no convective SIGMETs along that entire route. Another one is low-top convection. Anytime you get the tops of the thunderstorms or convection to be somewhere between 20 and 25, maybe up to 30, you won't have much in the way of lightning with it. So technically, they're not thunderstorms per se, but they can be dangerous from a convective standpoint, having a significant amount of convective turbulence. So sometimes you'll see convective SIGMETs issued for those, but in many cases they will not. Now, last but not least, we'll talk a little bit about how to minimize your exposure to convective turbulence. Here's some avoidance recommendations. The first one is kind of obvious, but I need to say it, is just stay out of convective clouds. Any vertically developed clouds, let's say more than 15,000 feet, 20,000 feet, you really need to avoid going into those. And you also want to avoid flying below any what I call healthy cumuliform clouds. Anytime the clouds get to be vertically developed, flying below those starts to add risk to that situation. As we'll see in a little bit when we're talking about convective outflow boundaries. So I try to keep blue sky above me whenever possible. Now, I'm not talking about a high-level cirrus deck, but essentially that vertically developed cloud that I'm flying under, I try to avoid that. If I can, try to go around that. So again, I have essentially blue sky above me. That will keep me, for the most part, out of most of the difficult situations with respect to convective turbulence. And one of the problems with convective turbulence is what are called outflow boundaries. Now, most thunderstorms have a distinguishable outflow boundary with them. Outflow boundaries essentially are the exhaust of a thunderstorm, with cold, dense air striking the ground and moving outward, away from the storm itself. So think about pouring pancake batter onto a griddle. That's essentially what an outflow boundary looks like. And it produces essentially what is a gust front. So outflow boundaries move away from the storm and produce this kind of gust front. Now, a gust front can have lift with it as well, as we'll see here by looking at this video. Now, what you'll see, this is the southern peninsula of Florida, and you'll see thunderstorms pop up along the coastlines here, maybe due to a sea breeze, kind of a front going on, and then you'll see the outflow boundaries progress from that. So you can see some of the thunderstorms develop on the east coast of Florida, and you can see outflow boundaries work out from those. And those boundaries themselves can actually initiate other convection along that. So it's real important to understand that those outflow boundaries can be actually pretty dangerous, not only just in the fact that they can produce other thunderstorms, but the outflow boundaries themselves are a big concern. So a gust front like this can produce strong straight line winds with kind of intense updrafts and downdrafts, especially within that first 2 kilometers of the atmosphere. And that's about roughly in the first 6,500 feet. So it's a ground hugging event. And what you see on the chart here on the right is a sort of a time elapsed representation of vertical velocities over a single point as an outflow boundary passed through the sensor field. Now the center red dashed line, anything above that you would have updrafts, and anything below that is a downdraft. So you can see time moves to the right. So on the very far left, time starting at 0 moves to the right all the way through to 8 minutes. You can see roughly around almost the 4-minute mark, you get a pretty significant updraft all the way up to 10 meters per second, which is roughly 23 miles per hour, or about 2,000 feet per minute. And then within less than a minute, there's an extreme downdraft that comes through as well. So you get an updraft followed by a downdraft. Now, if you're flying through this boundary, you're not talking about maybe 40 seconds or so. In that case, you're talking about seconds, because you're going at 150, 160 knots through this outflow boundary, you're going to hit the updraft and downdraft literally back to back. Now, these outflow boundaries can also be seen on the NEXRAD image. So if you look at the half a degree base reflectivity image, you may see something like you see on the right here as a crescent-shaped line that's moving away from the more intense cells. And this is especially the case when you're dealing with the radar image that's close to the radar site. In this case, the radar site's right in the center of the image. But it happens to be filtered by most of the radar mosaics that you can get in the cockpit, primarily because it's a very low reflectivity. You can see all the colors here in the blues in that outflow boundary moving south from Missouri into Arkansas. And it's also true that most of the radar images you can get in the cockpit are all composite reflective image. A lot of times those are masked out by returns out of the thunderstorm anvil as well. And when you look at that crescent shape and it's moving further south, eventually if we let this loop continue to run, it may look like the outflow boundary completely dissipates. But actually in reality, what's happening is that it's getting further and further away from the radar site, and the radar beams are actually overshooting it, so it makes it look like it disappears, when in fact it's just working under the radar. Remember, this is a very low-level event that's going on. So if you happen to spot any of these outflow boundaries on NEXRAD before you depart, and it's a good idea to look at that half a degree base reflectivity before you depart, probably a good idea to wait until that outflow boundary passes through you, or give it some time, because you don't want to be departing or trying to land essentially in an airport essentially to in this particular case, because you may end up beating the main precipitation line, but the outflow boundary there, you may find that you hit that first. The other thing is that outflow boundary, the reason why the radar is seeing it is that outflow boundary is a gust front, so it's picking up dust and debris, but it's also picking up insects. A lot of that is due to insects that is being picked up in that outflow boundary and moved away. And one of the things I like to tell all my students is beware of the benign when it comes to weather. Sometimes you think benign is a good thing, but for the most part, supercell thunderstorms are not really what kills pilots. It's those benign looking cells that lures pilots into danger. So be especially careful around high base thunderstorms. That's thunderstorms with a ceiling that is much, much higher. We're talking about 8, 10, 12,000 feet above the ground. Those dry conditions below the clouds leads to evaporative cooling, so as that essentially as the rain falls out of the base of that cloud, it starts to evaporate and makes it even cooler and denser and heavier, and tends to accelerate the downward motion. And so Delta Flight 191 out of Dallas-Fort Worth succumbed to a microburst event from a thunderstorm with a base of 10,000 feet. Again, even the professionals can get lured into thinking this is okay. And microburst happens so quickly with such force, it's really hard to overcome in those particular situations. So again, beware of the benign. All right, that's all I have for today. So to learn more, you can always visit the ForeFlight blog at blog.foreflight.com, or you can follow us on Twitter and Facebook. And if you want to learn more about aviation weather, you can visit my website at avwxworkshops.com. You can also follow me on Twitter and visit my YouTube channel as well. Now, this is Scott Dennstaedt, weather scientist at ForeFlight. Thanks for watching.